Hey, welcome. So, in physics, if you want to describe something like motion or a force, or really anything that has a direction, a simple number just isn't going to cut it. That's where vectors come in. And honestly, getting a handle on them isn't just a good idea, it's absolutely crucial if you want to ace your exam.
All right, here's what we're going to do. We'll kick things off with the basic difference between scalars and vectors. Then we'll dive into how to add and multiply them. And to wrap it all up, we'll do a super quick revision session to make sure the most important stuff really sticks. So first up, why do we even need to bother with vectors? Well, it all boils down to a really fundamental split in how we actually measure things in the world around us. Let's get into it. Okay, so here's the absolute heart of it. A scalar tells you how much. For example, a car is going 50 miles per hour. That's a scalar. It's just the speed. But a vector tells you the car is going 50 miles per hour north. That's its velocity. See the difference? One's just a number, but the other gives you the complete story. How much and which way. And you can see this in everyday examples. Your mass or the time on the clock, those are scalars. They don't have a direction, right? But a force, you have to push or pull in a specific direction. That's why things like force, velocity, and displacement are all vectors. They just wouldn't make sense without a direction. All right, so we know what they are, but how do we actually do math with them? You can't just add them like 2 plus 2, because that direction piece we've been talking about, well, it changes everything. This is the big idea for adding vectors visually. Just imagine this. You walk from your house to the library, that's your first vector. Then you walk from the library to the corner store. That's your second vector. The total result, or the resultant vector, is the shortcut. It's that single straight line path from your front door directly to the store. And this is how you actually draw it out. It's super simple. You just take your two vectors, line them up tip to tail, one after the other. The resultant is the path that connects the very beginning, the tail of the first vector, to the very end, the head of the second one. It's the most direct route. Now, drawing triangles is awesome for getting the concept, but let's be real, on an exam, you're going to need precision. And for that, we need to switch from drawing pictures to using a formula to calculate the exact size of that resultant vector. And this is it. This is the powerhouse formula, and it comes right from the law of cosines. Here, A and B are just the lengths of your two vectors. The really crucial part here is theta. That's the angle between the two vectors when you put their tails together. If you get that angle right, the rest is just plugging in the numbers. So, what about subtraction? Believe it or not, it's just a clever little twist on addition. If you want to calculate A minus B, you just take vector B, flip it completely around 180 degrees, that gives you negative B, and then you just add it to A, using the exact same head-to-tail method we just learned. Pretty neat, huh? Okay, so adding vectors is one thing when they line up. But what happens when they're pointing at all sorts of weird, awkward angles? Trying to add them directly can get really messy really fast. The much more elegant solution is to break them down into simpler parts we call components. So yeah, how do we deal with a vector that's just sitting there at some random angle? We use this incredibly powerful technique called resolving the vector. And what we do is we trade that one tricky diagonal vector for two much simpler ones that are way easier to work with. One that's perfectly horizontal and one that's perfectly vertical. Think of it like casting a shadow. If you shine a bright light from directly above a vector, the shadow it makes on the ground, the x-axis, is its x component. Now, shine a light from the side. The shadow it casts on the wall, the y-axis, is its y component. And those two shadows, those two components, perfectly add up to recreate the original vector. So how big are these shadows? Well, we find their size with a tiny bit of high school trig. Here, A is the length of your original vector, and alpha is the angle that vector makes with the positive x-axis. Use cosine to find the adjacent side, which is the x component, and use sine to find the opposite side, the y component. All right, time to level up. When we talk about multiplying vectors, things get really interesting. See, there isn't just one way to do it. There are two totally different types of multiplication, the dot product and the cross product, and they give you completely different kinds of answers. First, we have the scalar product, or as it's more commonly called, the dot product. Now, pay attention to the name, scalar product. The result you get is a scalar. It's just a number, no direction. This is super useful for finding things like work, which you get by taking the dot product of force and displacement. It basically tells you how much one vector is acting in the same direction as another. The second type is the vector product, or cross product. And again, the name gives away the secret. The result you get is a brand new vector. Its size depends on the sign of the angle, and get this, its direction is perpendicular to both of the original vectors. This is absolutely essential for anything that rotates, like calculating torque, and you figure out its direction using the famous right-hand rule. Now, looking at them side by side is where you really see what's going on. Notice how they're almost perfect opposites. If your vectors are perpendicular at 90 degrees to each other, the dot product is 0, but the cross product is at its absolute maximum. Now, flip that. If the vectors are parallel, running side by side, the dot product is maxed out and the cross product is 0. Remembering this little inverse relationship is a huge leg up when you're solving problems. Okay, we have covered a ton of ground. So let's bring it all back home. Let's boil everything down to the absolute must-know high-yield points that you are going to need for your exams. This right here, this is your ultimate cheat sheet. Everything we've talked about really comes down to these core ideas and formulas. If you can internalize how to add them, subtract them, break them down, and multiply them, you've got the toolkit to handle pretty much any vector problem they can throw at you. Look, this stuff isn't just abstract math on a page. It's literally the language the universe is written in. Whether you're trying to figure out the path of a baseball, the orbit of a satellite, or even the forces holding up a bridge, vectors are the tool you need. You now speak the language of physics. The only question left is, what are you going to build with it?